So we have seen that if you're given the intensity at 1 pixel in your image, that doesn't really give you a unique surface orientation PQ. We need to go further, and that's what photometric stereo does. What it does is that it uses multiple images of the object taken from the same camera location, multiple images taken under different lighting conditions, different sources. And this is a method that was developed by Robert Woodham, and it has been widely used, especially in structured environments. So we use these multiple intensity values measured at each pixel to resolve the ambiguity in surface orientation. So here is your setup. Again, we're looking at 1 pixel or 1 point right here on the surface, but the same algorithm is applied to every point on the surface. The assumption that we're making here is that the viewing direction of the camera is the same for all points on the surface, and the source directions are also the same for all points on the surface. In other words, the camera is far away and the sources are far away. Okay, so we're showing 3 light sources in the directions S1, S2, and S3. Let's assume that the point of interest right now has a normal N, and the viewing direction is, of course, V. So we have several light sources in the directions SI, that's PSI, QSI, each one of them. And for each one of these light sources, we of course are assuming we know the reflectance properties of this material, the surface. For each one of these light sources, we develop or we compute a reflectance map. That reflectance map is RI PQ. And now we measure multiple intensity values at each pixel corresponding to the different light sources, and those are I sub I at each point XY. And from these intensities we have measured and the reflectance map, we want to uniquely determine the surface orientation PQ. So let's see how that works. That's the basic idea. So let's now talk about a single light source, the first of these, S1. So let's say that this is the direction of S1, which is PS1, QS1, and we take an image of the object. Once again, we're looking at 1 point, but the same arguments apply to all points. And we have computed the reflectance map for the known reflectance and this light source. Remember, to compute the reflectance map, we don't need to know anything about the shape of the object. It's just computed and applied to all points on the object. So here's your reflectance map with its isobrightness contours, and we'll call that map R1, PQ. And let's say that at a particular point, we're going to fixate on 1 point, the brightness that you measure due to the source S1 happens to be 0.9. All the brightness values have been normalized to lie between 0 and 1. So let's assume it's 0.9. Well, 0.9 happens to correspond to this isobrightness contour. It has the brightness value 0.9, and it's telling you that all the PQ values, all the surface orientations that lie on this contour would have produced the same brightness value for that particular light source. So we have an infinite number of solutions. And now we're going to use a second light source, S2. So in the case of S2, we have a different reflectance map, of course, R2, because the source direction has changed. We're sort of overlaying the reflectance maps here for visualization purposes. And let's say this is the green reflectance map. In this case, at that same point, let's assume that you measured a brightness value of 0.7. Then that corresponds to this isobrightness contour. And this isobrightness contour intersects the previous one at now 2 points. So we have now narrowed down the orientation at that point, the PQ value of that surface point, to be one of 2, either this one right here or this one right here. So we're now almost there. What do? We throw in another light source, and that has its own reflectance map, which is the blue one right here. And it produces at the same point a brightness value 0.4. And that then resolves the ambiguity between the two solutions and gives you a unique solution right here. So that's the idea behind photometric stereo. And so let's summarize that. Essentially, you acquire K images of a surface, looking at the surface from the same perspective, K images with K known light sources. By known, we mean the direction, brightness, all of that stuff. So using the known sources and the BRDF of the surface, let's assume for a minute that we know the BRDF and it's the same everywhere. So using the known BRDF, we construct a reflectance map for each of those sources. And now for each pixel on the surface, XY, we find its orientation PQ as the intersection of K curves, reflectance map curves, and this gives PQ, and PQ, of course, yields the surface normal at that point. We know how to go from PQ to the unit surface normal N. Now, the smallest K needed depends on the material properties. It turns out that for a Lambertian surface, and here is a Lambertian surface right here, for a Lambertian surface such as this one, 3 light sources are sufficient to compute the surface normal at each point. We're going to talk about this and we'll see the reasons for this. In fact, we can go even further and even figure out the albedo at each point, but 3 is enough. Now, of course, the assumption is that each point on the surface can see the 3 light sources that you have used. If any of those light sources happen to be obstructed or outside the visible hemisphere of that point, then of course you're not going to be able to do photometric stereo. So you need the light sources to be separate from each other, different from each other, and yet close enough that all points on the object are visible to all 3 light sources, and conversely. So this is a Lambertian object, and for this it turns out that the number of sources you need to use is 3, and this is a special case and we'll explore it further. But then in general it depends on the complexity of your BRDF. Let's say you were looking at something that had both specular and diffuse components, you may need more. Let's say you were looking at something that is anisotropic, that might make things even more complicated. And the worst case, believe it or not, is the specular, the perfect mirror case. Remember that in the case of a perfect mirror, for any given point light source, there's only one viewing direction from which you're going to get a reflection at any given point. And therefore, you can argue this out with yourself, you can convince yourself that you would need an infinite number of light sources to measure all the surface normals on a perfect mirror, if it is a curved mirror such as this one right here.